Hi, here is Luaksz Dywicki and welcome you on my talk Apache PLC4X for CAN bus and CANopen. This is part of IoT and IIoT track in ApacheCon Asia. So today agenda is composed from several big items. So the first introductional part is about our interest in IIoT, our meaning the IT indeed, and then I will introduce myself and CAN and CAN bus systems. Then we will do an overview of Apache PLC4X APIs, followed by generic purpose driver, which is, I believe, one of most recent additions to the project, together with CANopen and CANopen usage together with Apache PLC4X. So a short note, this talk is intended mainly for IT audience. So if you work closely with CAN and CANopen, you probably know already more than I, and more than I will be able to present here. But if it would be very kind if you could leave a comment if you watched the movie afterwards with your feedback about the presentation and its contents. And if you find something misleading which requires clarification, then please send me a message using the email address which is on this slide. So why we are interested in IoT? So first and foremost, this market will grow, and different estimates say that it will grow roughly double every 10 years. At least the next 10 years will be like that. And this means that there will be a lot more devices coming to the market. And beside that, we still have industrial devices which were developed prior industrial Internet of Things have been invented, let's say. So some systems and the move of them is still very expensive, so they do require a brownfield kind of approach. And also we have standardization requirements and legislation which we need to follow in IT in some areas. And well, definitely IoT as a younger market will grow faster than big data, and places where Apache PLC4X can help are following. So because market size will increase, new devices will be deployed, we need a unified API which allows us programmers to talk with different equipments, with different hardware, with single and quite stable APIs. And I believe the Apache PLC4X does ship that, and we will talk briefly about that. The next point is really an expensive part of industrial Internet of Things. I mean, it must be safe, and the old devices aren't that safe, especially that they lived in the silo kind of organizations and separated networks. And this industrial Internet of Things actually changes that. So industrial machinery is no more alone. It is running quite often close to the office networks and so on. So making a secure connection between those systems, especially old ones, is not possible. And so we need to take care of the older equipments and integrate with them as well, because no one will change $1 million expensive machinery just to add one or two connection possibilities. And the standardization requirements will follow probably because each jurisdiction will have its own approach towards the law and law systems which regulate the IT field and OT. So the growth of the IoT will also be able to stem a little bit the big data. I mean, you can always source the industrial data and feed the big data systems, making those even richer. And how Apache PLC4X can help? So especially because this is a unified programming interface for various hardware and protocol, this itself is a big advantage over the different approaches. So it allows you to use different protocols using singular API, which is quite straight and does not have any corner cases. So the next point is the SPI. If the existing APIs or provided mechanisms do not work, you can always use the SPIs, meaning the software provider interface, to make your own adjustments. The third point is really about library part of the Apache PLC4X, because it does ship a set of the drivers. These drivers are tested and used by several entities, and those cover Modbus, S7, Siemens S7, backup ADS, Ethernet IP, as well as CANopen. We also have the OPC-UA support, which is receiving right now very big updates. So by using Apache PLC4X, you can access these protocols and this machinery fairly easy. The fourth point is toolkit nature of the Apache PLC4X, which allows you to build your own driver. Meaning, if there is something which is not supported by the project, it's not a problem to add a new driver. And the fifth point, which is still forming, is a framework. Apache PLC4X and some parts of the APIs can be used to build a rich applications which not only access industrial equipment, but can discover it, can configure themselves, and build a lot of additional functionality on top of the mechanism shipped by it. So who I am a guy who visited China several times, but first and foremost I'm Polish. I'm working in IT since 2005, since I was 19 years old, and most of my professional career is related to open source. Since 2010 I am committer in Apache Karaf project, and since a few years I'm also committer in Apache PLC4X. So I'm also an independent software contractor, so I work in my own company, and I also founded a product company called Connectorio, where I did author several OpenHub add-ons, and some of those rely on Apache PLC4X. And for example, this is a screen of OpenHub running Apache PLC4X CANopen integration, and some configuration interfaces which are available via OpenHub itself. So I got into the project really somewhere around 2018, thanks to Christopher Dutz, who let me know that actually he began working on some industrial thingy, and based on my prior experience with OpenHub and BACnet, he asked me to follow. And so later in 2020 I began experimenting with link layer discovery protocol and also Profinet DCP, which eventually led to implementation of CANopen. So let's talk a bit about CAN. So the CAN bus is a specification which was initially published by Robert Bosch. This is a company which did look for a solution in the mid-80s to introduce fairly cheap and affordable way to connect car peripheries, and they did find out this way and published the CAN specification in the late 80s, and later there was an update and 2.0 release, which was published first in 1991, which became an ISO standard in 1993. So the most recent release of CAN is CAN FD, which was introduced in 2015, and this is still CAN, but it changes a lot in terms of how it works, and one of the additional parts which is currently in works and under the standardization is CAN XL, which is first published and officially started in 2018. So few key points about CAN and its characteristics. So it's a multi-master digital bus system, meaning you can have multiple nodes trying to access bus at the same time. Some of them might write, some of them might receive data. It doesn't really matter how it is constructed. Your application which utilize the CAN bus itself and microcontrollers, transceivers actually, can detect collisions and also stop publishing the message if there is a high priority message already written to the or at the process of writing to the bus. So this multi-master nature has certain advantages, and lack of this explicit master-slave relationship, which we know from Modbus and Profibus and other bus systems, is quite unique. And the thing which I did touch in the previous paragraph is really about the arbitration. So each message which is published to CAN bus has an identifier, and this identifier is used for prioritization of messages. So the lowest identifier wins. If two nodes, two CAN nodes are trying to write to the bus, the one which writes the message with lowest priority will win, and the second node should stop from continuation and wait for another cycle to write the message. And because of characteristics, CAN can also provide some time determinism, which is important in some applications. And the major CAN usage nowadays is definitely in automotive industry. This was the first sector which was served by it, and it is served till those days. And different standards cover usage of CAN and CAN bus in cars, trucks, and special purpose vehicles. And for example, in the European market, there is a standard called OBD. I believe this is onboard diagnostics, which is mandatory for every new car which is released in the Europe. So another sector which is reaching the CAN and CAN bus solutions are robotics, input-output modules, which are used in the industrial use cases mainly because of the possibility to use CAN in harsh conditions close to the magnetic field, and also with motor controls. And for the input-output modules and motor controls, we have CANopen and corresponding profiles which describe how these devices should behave. CAN is also used in buildings for escalators, for lifts. Actually, most of escalators use somehow CAN. However, it's quite hard to find a countrywide standard in this area, so it can differ from country to country. And beside that, CAN is also being used in a heating system and some smart home systems, mainly because of the simplicity of the viewing and ease of diagnostics. Another part where CAN is also dominant in use is energy and mobility, mainly in the battery management systems, because these areas use extensively CAN. Some usage is also reserved for railways and aerospace. However, there are very little publications about that. And CAN is also used extensively in the CNC, in the milling machinery and so on, mainly because its safety features, which can be used, for example, the stop machine, the spinners and so on, are quite important, and also the motor controls can be built with the CAN. So there are several versions of CAN already in the market. There is a CAN 20A, which is published at the same time as 20B, and this version of standard is from 1991, so it's quite old. And the difference between CAN 20A and CAN 20B is the length of the identifier. So this arbitration, this is sometimes referred as arbitration field, but this is also noted as an identifier. So both CAN 20A and B have from 0 to 8 bytes of data, and the difference in identifiers gives a more fine-grained way to do arbitration. Both 20A and 20B can go up to 1 megabit, and the more recent releases like CANFD and CANXL can do much faster. And the CANFD expands to flexible data rate, and this is this most recent release of CAN specification, which allows to use the burst transmission during the data transmission phase. So we can pass within the same time more data, and so the length of the data block in the CANFD frame is bigger. And for CANXL it's even higher, and it goes up to 2048 bytes. And the main idea behind the CANXL is to let it be used as a transport mechanism for wrapped IP packets. So this means that it will be possible to reuse CAN infrastructure for IP networking, and the speed of the network of CANXL network is up to 10 megabit and even faster. It's not yet measured how fast it can go. So most of these standards are somehow compatible. For example, CANFD and CANXL can be used in the same network. Similar with CAN20A and CAN20B. I mean, most of the microcontrollers which does support 20B can also support 20A. So it's more or less configuration and not the hardware feature. And if we look on the OSI layers, then from IT perspective, we have several things which we know very well, like DNS and HTTP, but those are the highest level of the OSI layers. So these are the so-called application protocols, and rarely, but still in IT, we refer to TCP, UDP, and sometimes IP. But very, very rarely we really talk about MAC and Ethernet and the cable-related part, which is actually a physical network. And because all operating systems do standardize the network stack, so handling of the MAC addresses, Ethernet frames, IP frames, and TCP, UDP transports is implemented within the system, we do not bother much about those and how those are being made. So our applications are built for concrete operating systems, and they work with the tools which are provided by operating systems, meaning that we build our applications and our protocols with assumption that the network will work. And this is quite different for CAN, because depending on the operating system, we might have standardized network stack, let's say, or not. For example, on Linux, we have a socket CAN, and socket CAN is kind of network stack. I mean, I don't want to overestimate it, but the socket CAN does unify various kinds of the hardware which can be used to access CAN bus, and so different suppliers of CAN modules can write drivers which do contribute to socket CAN instead of writing their own drivers. On the other hand, for Windows, we have a different situation. So usually hardware adapters ship their own interface, which is based on the serial API or some other mechanism which are not standardized. So this is a big difference, because it does impact how we write the integrations which do rely on CAN, and in most of the cases we cannot run out of specifics of the hardware which is being used. And if we will have a look on Apache PLC4X and how Apache PLC4X does map the OSI layers, we will find that the top layers go to the top layers are handled by driver and protocol, while the low levels from transport down to the physical are wrapped in the transport. So because the Apache PLC4X works with the operating systems, I mean, it's not embedded, it can be embedded in the microcontrollers, but its APIs are not intended to implement system specific parts. Those are rather the APIs of the Apache PLC4X are intended to unify the most common situations related to the integration. And this means that, for example, delivering the data stream and then turning the data stream into concrete information which is according to the protocol. And now a very quick look on the Apache PLC4X API. So there are several parts which we can outline. So there is an SPI which allows to wire in new transports. There is a toolkit part which I did mention before. This is an MSpec message specification which can be used to generate the code and then be used in the driver and protocol implementation. So these are there. The driver and protocol does define the field, and the field is really an information how to access the data in a given protocol, and the field is specific to the driver, and our application needs to use a valid syntax for a field. So even if there is no direct linking between the user application and the driver, the field syntax is different between the drivers. So our application, if it wants to interact with the hardware, it can use several APIs which are available in the Apache PLC4X. This is the read-write, subscribe, metadata, browse, and discover. And those are covering different aspects, and not all drivers support all of those operations. So this is the set of public APIs, and drivers, depending on the possibilities, they can ship or cannot ship those. And the root we start from interacting with the driver manager, which allows us to obtain connection to the hardware. And a few important points. The driver is an implementation of a specific protocol, and it might utilize generated structures but does not have to. So it means that it's possible to implement a wrapper using the Apache PLC4X APIs and use the third-party libraries, and that was the case for OPC-UA driver in our project for past releases. But the root responsibility, or the prime responsibility of the driver, is to define wire-related operations, like what is the root frame of the expected by the protocol, and which transport should be used, and how this transport is being utilized. So the driver is wrapping up not only the protocol but also have to touch a little bit of the transport. And for most of the IP-based drivers, it's almost a transit operation. And the next key point is a field. As I said, it's quite specific to each and every protocol, and you can think of it as a coordinate to access data available via a given protocol. So it's definitely a driver specific, and for example, here you can see a generic CAN field information. Here is the CANopen definition, which defines the sub-protocol used in the CANopen, the node ID, the index and subindex, and also the data encoding, which is expected to be on the other side. And the last example is actually back of ADS field syntax. So as you can see, the differences can be significant, and your application must know a bit of the about the device in order to construct proper fields and request proper data. So fields are used in most of the interactions with Apache PLC4X because this is the coordinate which tells the project, the library, which data the application wants. And it does imply in many cases the data type returned to you, but also wire encoding. And this is an example of a code which is used to access this is an example how to call the driver and retrieve the data over CANopen. So here you can see that there is a connection string which specifies the driver, the transport, the interface name, and also some driver or transport specific options. So the node ID in this case goes to CANopen driver. Then we construct a read request, add the field. This the item, the first argument here is the alias, which we are using to later on to retrieve the result. This is a field syntax, which I did explain briefly before. And then we build the request, call and execute, and await for response. And response can be either success or an error, and if there is an error, then we should get stack trace, and in the end we can also call the result and display it to the user. So few notes. As you can see, most of the API calls, at least in Java case, are using Java 8 completable feature. So it does promote asynchronous practices for read and write, and this means that your application must be aware that some actions might not be intermediate. You have to block explicitly if you require an intermediate action. So for many places we make an extensive use of the build pattern, so it allows you to construct the requests and process them in very convenient way, and almost all interactions with PLC4X will rely on fields. And now let's have a look on generic CAN driver and how this syntax, the driver, the transport, and the fields can be used to access CAN frame. As we know, the CAN frame can have from 0 to 8 bytes of data, and in this particular case we know that it's possible to write to the bus, but because CAN bus does not have any explicit syntax about the reading data like request response, the read operation is not supported. So we can write and subscribe for messages coming from the other end. So this is quite different from many other drivers where you can read and write data, but here in this case this is a generic proposed driver which does not know how to implement the read requests, and in fact there are things called remote frames for CAN, but those are not recommended for a new deployment, so we are not using it in any explicit way. So generic CAN driver have to know how to construct the frame, and so the fields which we are using for write and subscribe calls, they do define a frame structure. So the application needs to know what it expects to receive or what it wants to write, and construct it using the field syntax. And the field syntax is based on the node ID, type, and the eventual ID array size. So by using the proper order of the calls, we can construct a concrete frame. So this is a generic code which uses a generic CAN driver and writes to the bus. As you can see, there is 3 fields and one node 200 which is used, and the frame will contain a static part, two static elements, and then one counter which will be incremented and resetted from time to time. And the subscribe call looks very similar. So we do define fields, and as you can see, the field naming is different because this is the other part or other side of the communication. However, the order of the fields which are defined is the same, and they do also use the same node ID. And the difference is that in the end we get a subscription handle, and this subscription handle is called each time when there is a message on the bus. And this subscription handle is quite simple. It does take a subscription event and writes out all the fields which are part of the event. So now we can have a look how this looks alike. I will start from watching the bus. As you can see, this is a standard Linux utility, and now I am starting the subscription, and as you can see, it does not generate any traffic on the bus because subscription is a client side thingy. And now we will start writing the data, and here you can see we get in the output the counterpart of the frame. So apparently it works, and the driver, the writing part does work, and it does publish the messages. And now here we we see it also receives the data. So we have a field name, the value, and here you can see that it does increase the counter. So moving forward, this syntax is very simple, and as you can see, we wrote a semi-generic application which interacts with CAN with just, I don't know, 10-20 lines of code. So it's quite basic. And if we will have a look on the canvas traffic, we will see the interface name, the direction of the communication, so transmit or receive. And since I'm using the virtual interface over the socket CAN, it doesn't really matter. But if we would have two physical nodes which are accessing canvas, it would matter, because on one side we would have TX and on the other the RX. Here we can see a hex of the node ID, the size of the data, and you can notice that the data is set to 8, but this is mainly because of 0 pad added by the socket CAN. So we have the 055, which is the static part of the frame, the another part of the static frame, and then the last part, which is the counter. And so you see that with generic approach we can support some applications like read and write. And the CANopen is very old standard how to build the automation systems with CAN, and it was published in 1994 as so-called CIA 301 or CAN in Automation 301. This is the document which was initially again maintained by Bosch, Robert Bosch GmbH, and was released and formed actually one of the first vendor-independent field buses, because back in there in early 90s there were very few systems which could offer functionality such CAN did. So it gained some adoption, but clearly there was no standards how to read, write or broadcast data. So CANopen did define these protocols. It also did define encoding of the data types, and beside that it also did introduce the object dictionary. And the object dictionary is a list of the addresses which should be used for read, write and broadcast operations. And the dictionary is integral part of the CANopen spec, and each CANopen device does have the object dictionary. So sometimes it is referred as OD, like in the shortcut. And by the design, CANopen network can have up to 127 nodes. And if we will have a closer look on CANopen, it does use the 11-bit identifier of CAN frame, and first 4 bits are used as the CAN service identifier, and this gives the first 4 bits a major take in the prioritization of the messages. The following 7 bits from the identifier are used for node ID. So on the 7 bits we can encode up to, I believe, 127 unsigned number, and these two things together serve a full CAN identifier. And the services and their priorities are following: the NMT, this is a network management, and it does define the ways how the nodes can broadcast their state. Like if they are ready to be activated or activated, they should broadcast that. And this is this is actually one or two broadcast or request reply protocol. Then we have a sync, which does emit a synchronization frame, which other devices should use to adjust. Emergency, time broadcast, process data objects, PDO, SDO, and HERPAD. So from those, the ones which are most common or happen most often or are most useful, are PDOs and the SDOs. And there are several data types which are supported by CANopen, and obviously there is a boolean which takes 1 bit. There we have numbers of different sizes from 8 bits to 64, and we have also floats and the byte array, which is called a record, and the encoding of the record depends on the device. So the record itself is a sequence of the data which needs to be interpreted according to the object dictionary. There are also time-related types which are currently not implemented in Apache PLC4X, and also text-related types. And using the CANopen object dictionary plus specific addresses, the CAN in automation does define profiles, and these profiles define again additional pools of the addresses, and these addresses can be used in specific devices or applications to build solutions. So quite often CANopen profiles, they do define also a behavior of the CANopen nodes, and these profiles are actually a base for device certification in certain directions. And CANopen in Apache PLC4X is implemented partially, so we do not support all of the services, and our implementation is more focused on the data acquisition and some basic interactions with the CAN devices, but it does not implement a full CANopen device as it is defined in the specification. So we do have a support for process data objects, so PDO can be either receive or transmit, those are broadcast messages. We also have SDOs, which are read-write operations. So as you can see, while we do not have read-write operations for generic CAN, we do have read-write operations on top of the CAN bus using a CANopen. And beside that, we also have a support for Herbert and node monitoring. And the field syntax for CANopen is service name, node ID, and then protocol specific part. So depending on the specific service, we might have different parts. For example, for SDO we have index and subindex, so those are object dictionary defined verticals. And then for the transmit and receive PDO, we have 4 groups which serve as a prioritization, and then the node ID and the type of the data expected. And for node monitoring, we have either the monitoring for all of the nodes or specific node. So in real life, really, if we would like to start with CANopen, we need to get first a compatible interface with the CAN. So on Linux, obviously, this is a socket CAN, and it's easiest to get and to start with, because there is a wide selection of the compatible hardware. And then that there are several other aspects. So we need to know how to read and write data, and for receiving only we can use easily PDOs, because this is a process data, and the process data is most interesting in most of the cases, because this is how we do the analysis and things like that. And the SDOs, on the other hand, are used to read-write data and configuration. So it is still used, and some systems might use it also to transmit process data, but it's far less effective, because the PDO is does occupy a single message on the CAN bus, while SDO, the smallest SDO transaction on the bus, will occupy at least 2 messages. And if we would like to pass 8 bytes of the data, which fits normally into PDO, we need to use 4 frames on the CAN with the SDO. So as you can see, there is a severe impact on the CAN bus. And now a few words how the CANopen, generic CAN, and CAN transport can work together. And this is really a unique possibility which was updated, because first time when I did work on CANopen driver implementation, I did merge it actually with the socket CAN frame shape. And recently I managed to separate those, and so now we can have a generic drivers, generic transport, we can have CAN based transport, CAN application layer implementation like CANopen or OBD, and they do not stick with specific hardware and the specific microcontroller to interact with. So it usually starts from the wire and from the trans receiver and the CAN transport which can talk to this specific hardware and access the bus. Then in case of socket CAN, it is being transformed into the socket CAN frame, and it is being passed through the conversation wrapper, and this conversation wrapper is part of the SPI for Apache PLC4X, which is used by each and every driver to receive or send data. So this wrapper does the transformation, and it does use the frame handler, which is defined by the driver to map CAN frame to protocol frame. So the main difference is that each CAN transport can have a different representation of the CAN frame, which is specific to the microcontroller which is used for that. And each protocol, on the other hand, can still use its own root frame, and there are no common parts. So this transformation layer allows to use any CAN transport with any CAN driver. And obviously there is an impact on the performance, but for data acquisition scenarios it's not that relevant, I would say. And moreover, it allows us to implement faster drivers and do it in reliable way, because each driver, like CANopen, can have its own syntax related to the processing of the data, and does not have to worry much about the CAN frame itself. So if you find it interesting, then please leave your questions and I will try to answer those. And remember, if you can, then you can always visit Apache PLC4X website. You can also find me in the social media, and well, I wish we can meet on Apache PLC4X mailing lists and cooperate more. Thank you for your attention.